Alright, I guess I will take that as a no. But if you do come up with any questions at any point, just, stop me. So, let's just take a look at some of the ones I pulled out of the textbook, I guess. So the first one I got is kind of similar to one we did last week, but I just figured it would be a good idea to do another one. And Dr. Fonseca suggested it too. So we have this up here, this top part is figure 3.4 that's mentioned down here. So these are like two different images. So we have some machine where it's every word is 16 bits. And if we have an instruction, the first 4 bits are going to be the opcode, and then the remaining 12 bits are going to be the operand, in this case, an address. And then we just have this one here, which is just an integer, so the first bit is the sign, and then the rest of it's the mantissa. So, this machine has 3 opcodes naturally in the diagram, so it has this one, and I'm going to write everything in hex, so you'll notice here in blue, hopefully I can zoom in on it and make it a little bit easier to read. We have hex 1 is the opcode for load the accumulator from memory, then hex 2 is store accumulator to memory, and 5 is add accumulator to memory. And then so down here in the question 3.1, we have given this hypothetical machine with this opcode here and 16-bit words. We have 2 other opcodes on top of this one. So this deals with actual memory, like RAM, and then this one has an I/O, so maybe a hard drive or like a flash drive or whatever. So we can also load the accumulator to an I/O or from some sort of input. So in these cases, the 12-bit address identifies a particular I/O device. So again, the 12 bits are the last part of this is just the operand and the first 4 bits of the opcode. So in this case, the operand is an address. So we want to come up with a way to load the accumulator from device 5, which is an I/O device, add the contents of memory location 940, which is in actual main memory, and then we'll store the result to I/O device 6. So this shouldn't be too bad. So does anybody see what opcode we should use if we want to load the accumulator from device 5? In hex? Hex 3, right? So that'll be and actually I wrote 03, but I guess I should have just put 3. And the reason I say that is because if you notice here it's 4 bits, right? It shouldn't be 03, it should just be 3. That's my bad. So all these, ignore the 0 out in front. I was writing it as a byte, but these are just 4 bits, they're nibble, right? So that'd be the opcode. And then what's the operand? So what are we going to do? So this is the load part, right? And then we need to do it to device 5. So just remember, this will be 16 bits, right? I probably should have written that in green. So this first part is 4 bits, so the remaining part has to be 12 bits then, right? So if I want device 5, what's that going to be if it's 12 bits long? .005, right? Okay, so somebody said it. So this would be 12 bits, right? Assuming this is all in hex. So the first 4 bits are the opcode, which was 3, we saw here, and then the operand in this case is device 5. So 005, just to make sure we fill out the whole word. Cool. Good job. And then if we look at the next line we want to do, we want to add the contents of memory location 940. So this is already put into the accumulator. The accumulator over here has the contents of device 5 now. And now we want to add memory location 940 to it. So what's the whole operation going to look for that? So what's the opcode and the operand? So first off, the opcode would be 5940. Let's see. So 5. Oh, sorry. I guess I should probably move that a little bit over. 5 is add to accumulator from memory. Good job, right? And then address 940. Yeah, you got it. Exactly. Cool. And then we just have this last one, so we want to store that result. So now the accumulator has whatever that was, device 5, oops, plus 940. And then the last thing we want to do is we want to take that result that's now in the accumulator, right? And I think somebody's already ahead of me. Good job. So 7, is that it? Store accumulator to I/O, right? And then device 6, right, which has 12 bits, would be 006. Cool. Good job. That looks good. All right. And then again, consider all of these. I did write it in different colors, but these are all just one long 16-bit string. Any questions on that one, or does it seem pretty straightforward? Pretty easy. Looks good to me. Okay, fair enough. Go up to the next one. I think I had one thing. Oh yeah. So this one wasn't a question. I just thought the diagram might be good to look at. So this is figure 3.5 in the book. So somewhere in the chapter, I think for some reason they didn't even like specify the whole thing. But there's 3 parts. The book says 2. 2 parts to an instruction, or the way an instruction is like processed. So can anybody list either the 2 the book gives or the 3 steps that a instruction is going to have to go through for the processor or to be processed? And notice everything in this column is actually one of those instructions. The other one is the other. Or not instruction, but, process. Fetch and decode, so that's 2 of them, right? And they actually skip decode for some reason in this one. But yeah, you're right. So this one over here is the fetch part. And then, what is that part? Yeah, execute, right? So they skip the decoding part, I guess because it's not super interesting in the context of this, because nothing would really change. But yeah, we want to fetch, decode, and then execute. Code. Execute. And just to briefly explain that, fetch just means to get the instruction out of wherever it is, whether that be the cache or main memory. Decode is figuring out what it actually means, so figuring out, oh hey, this is what the opcode corresponds to, this is what we should actually be doing, and then execute is the actual, running it through the register, doing whatever it is that the opcode actually corresponds to. Cool. So if we just take a quick look at this really quick, the way they lined it up, these are all the fetch and these are all the execute. So first, what we do is we have a register in the CPU called the instruction register. That is, we have the instruction register and the program counter. So I think we should look at the program counter first. The program counter tells you what address in memory we are in terms of instructions of the program. So the program is just a block of memory, right? Possibly multiple, that correspond to some instructions. So this will just tell us the address to get an instruction from. So we start at address 300, and we go and we fetch from memory address 300, and we take the instruction that's located there, which is 1940, and we put it in the instruction register. And then on the next cycle, all we have to do is execute that actual instruction in the register. So this one corresponds to the same opcode that we had earlier. Let me just drag it over. I don't think I can erase this either. Oh well. I think everybody gets the fetch, decode, execute. Hopefully I can just cover it up. We'll just pretend it wasn't there. Okay. But yeah, so this diagram corresponds to the same opcode from this one. And again, ignore the extra 4 bits that I put in front. So the instruction is 1-940, which is similar to what we just did, I believe, right? We had 5-940. So what we're going to do is we're going to do 1, which is load accumulator from memory, and we're going to load 940, so that's the actual operand in this case. So again, this part is the opcode. This part is the operand. So this one says load accumulator, load into the accumulator from address 940, which is the number 3. So it just loads from memory, puts it into the accumulator, and then we begin again. So we fetched, we executed, we're going to fetch the next one. So the program counter, if you notice, went up because it executed or fetched an instruction from that address. And then it's just going to automatically increment and go to the next address. So it goes from 300 to 301. And then, again, it's going to fetch. So it's going to fetch at 301 this word here, 5941, and put it into the instruction register. And then we go to the execute part. So it executes it, has opcode 5, which was add to accumulator from memory. So this is going to take the accumulator, which was previously 3, and add address 941 to it. So it takes 2 and adds it to it, and now the accumulator has 5 because it stores the result. And then again, the program counter is going to go up because it executed an instruction. So we go to the next memory address, 302. We fetch it. So again, this side is fetch. We store it in the instruction register, and then we execute it. So this one in this case is 2, which is the opcode store accumulator to memory, and then it's store address 941. So we take the accumulator, and we're going to store it at memory address 941. So really, this whole long thing is just the code x equals x plus 3. This whole long thing is just that. Is there any questions on... Oh, thank you. Yeah, if you just joined, remember to post something in the chat so I can take attendance. Any questions on any of that? Does it make sense that the first bit on this specific machine is the opcode, and then the rest of it is like what it's operating on, and that we have 2 different cycles here, fetching and executing? Cool. Bunch of yeses. And if you have questions, don't be afraid. All good. Okay. Fair enough. And again, stop me at any point if you do have a question on this. I just figured that one would be good to go over because I know I was a little confused on that when I took this class. Oh yeah, so this is one Dr. Fonseca told me to go over. I think it was phrased really strangely, this one. So I'll try to explain what they mean, I guess. So this one's 3.6, if you didn't see it. So consider a computer system that contains an I/O module controlling a simple keyboard printer teletype, so some sort of machine. The following registers are contained in the processor and are connected directly to the system bus. So we have an input register, which is going to just take stuff from the I/O module, in this case the keyboard. We have an output register, which is going to take stuff from the printer. or give stuff to the printer rather. It'll wait there and cache it until the printer is ready to take it. We have an input flag, which just says that the input register is ready to be read from. And we have an output flag, which says that the output register is ready to be written to. And then we have an interrupt enable. So keystroke input from teletype and printer output to the teletype are controlled by the I/O module. The teletype is able to encode an alphanumeric symbol to an 8-bit word and decode an 8-bit. Yeah, so this is just extra stuff. We're assuming that it knows what it's doing. If you hit a key on the keyboard, it's already going to take care of turning it into ASCII for you. You don't have to worry about that. The processor's not going to have to do that. The actual I/O device is doing it. And then the same thing with the printer. It can figure out what the ASCII is and then, print it. Okay. So we want to describe how the processor, using the first 4 registers listed in this problem, can achieve I/O with the teletype. So this, I think, was really vague. I had to think about it for a while. But I think I actually accidentally kind of explained it when I was talking about those. So what is going to happen is the keyboard, so we have a keyboard over here. We have a printer. And then the keyboard is going to have access to probably 2 things, if anything. Yeah, I don't know what a teletype is. I don't know if I'm just not old enough to understand that or what. Or if I just don't know. So we'll take, let's just say the INPR, so the input register. So we'll give that access to the keyboard, or keyboard access to that rather. And then the FGI, which is 1 bit. Should maybe make that a little bit bigger. FGI. And then likewise for the printer, we'll give that the output register. The output register, and then the flag for the output register. And then, yeah, we'll wait on the interrupt thing for later. And then we just have the CPU, which can see all this stuff. So what we want to happen is we don't want the CPU to be waiting too long on the keyboard or printer. So we want it to just be executing all the time. So what's going to happen is every cycle, the CPU is going to do a couple things. So A. So the CPU is first going to check the FGI. And so, again, that's just the input flag. So it's going to check, is that 1? If it's 1, then it's going to stop what it's doing, and it's going to deal with whatever's in the input register. So there's probably an actual instruction there with opcode and an operand, and it's just going to take that and put it in the register. Or possibly it's just going to take the 8-bit ASCII character, and if not. And then if there's a 0 in the input register, then that means that there's no input to be taken. So it's just going to just keep going. And then after that, apparently teletype is the actual device that sends receives typed messages. Oh, you learned something new. Actual devices. Is that built into the motherboard, or is that part of the I/O device? I presume the motherboard, right? Either way, I guess we'll come back to that. Thank you. Yeah, so it'll check the input register. If we have something, it will read it and then pause what it's doing, save it for later possibly, and then if it gets a 0, it's just going to keep going with what it's doing. and then, oops, not B, and then it does what it's doing, executes, whatever, and then it will then check the output flag register. And again, if that one's a 1, then it will handle whatever request is being done there. And then if it's a 0, it keeps going. And actually, one other thing that's going to do, I remember from the answer key, and it makes sense, is if it reads a 1, it's going to handle the request and then set the input flag to 0. So basically to acknowledge that it actually got the input from the keyboard, so the keyboard can again figure out what it's supposed to do. So if the keyboard sees a 0, then it knows it's safe to load stuff into here because it's already been taken or it just hasn't been set yet. And then likewise, same thing with here. If it reads a 1 out of the output flag, it will say, okay, I've got it, take the contents of this register, and then set this flag to 0. Does that all generally make sense as a way to set this up for input output, is just wait for a flag and then check it every single cycle? Okay. And then, so they give another one, describe how the function can be performed more efficiently by also employing the interrupt. So, I guess every single cycle we're going to have to check both the input register and the output register, a flag, and they're, on an actual machine there might be a lot of these flag registers to check. So instead, a good idea is to, and what an actual computer should do, is to use the interrupt register. And then there's probably some associated register with that everything, I mean, realistically, there's probably one system bus that these all connect to. It's probably more like this. So whenever this needs to do something, it will send an interrupt, or whenever this needs to do something, it will send an interrupt. So we only have to check, in that case, the I interrupt register, which is one bit, just true or false. Is there an interrupt? And then it will decode whatever that is, and then figure out what to do with it. So in this first example, these are specialized registers, so it doesn't really have to do much decoding to figure out, well, the INPR, that corresponds to the input, and the out register corresponds to the output. When we have an interrupt, it needs to get an interrupt, and then realistically, there's probably another register that has information about the interrupt, some sort of encoding scheme for what it corresponds to, whether it's a exception or whether it's it needs to write to output, or if it needs to read from input. There'll be something that tells it what to do. And so you'll see that B is generally more efficient, even though it has to do that extra figuring out. If you have a whole bunch of things, it kind of saves time to do that. So that's realistically what a computer will do. Does that all make sense for that part too? Why you would want to use an interrupt over just checking everything every single cycle? Yep. Cool. Okay. So I think we'll move on to the next one. I think I did an example really similar to this yesterday. And they want us to consider this just for chapter 4, but if you have a different answer, just, don't be afraid to say it. So we have these two programs. Which one is better and why? First one. Okay, so I see everybody saying the first one. Less cache misses, so that's going to be part of it. And then the cache missing part is actually due to something else. Yeah, which I see somebody saying. So we have the cache, and then this one was from chapter 4. So the explanation they were looking for, which I'm seeing a lot of now, is this one has temporal locality over this one, which aids in the cache hit versus miss. If you have temporal locality, then you're going to be likely to get cache hits. And then just briefly, I know everybody's saying temporal locality, and you're all right. The reason that is right is that we're using z of I here, and then we're using it again immediately. So it's likely, we're going to use it one after another, so we don't have to update anything with memory addresses. And on top of that, right, like everybody's saying, then we're more likely for z of I to be in the cache than over here, where we're going to keep putting x, y, and y. We're going to be kind of hurts to look at. Yeah, I mean, I think naturally most people are going to want to program it this way versus that way. But I mean, realistically, they are doing the same steps, right? There's no extra instructions. So just from a baseline, there's nothing wrong with this. Just strange. Okay, so I think that one was pretty clear. Just figured it would be good to bring it up. And then the last one I have is figure 4.5. Let's make that a little bit bigger. Good enough. So consider an L1 cache with an access time of 1 nanosecond and a hit rate of 0.95. Suppose that we can change the cache design such that we increase H to 0.97, so it hits 97% of the time, but increase access time to 1.5 nanoseconds. What conditions must be met for this change to result in improved performance? So I guess one thing we want to consider here is this feels like it's missing something, and what is that? Does anybody have a guess as to what would help us here? Number of accesses? Potentially. Transfer rate? You're on the right track, but a little bit more specific than that. Yeah, actually, number of accesses would probably work. Maybe, actually, I guess with the ratio, I guess it might average out. So it has to do something with transfer rate, and it's something that they didn't mention at all here, but it's something we have to consider. So what happens when we get a cache miss that makes it so much slower? What does the processor have to do if it has to keep looking, right? It has to check. Oh, there we go. Somebody said it exactly. It has to check main memory. So if you remember, and let's ignore L2 cache and L3 cache and all that stuff. If it misses cache and doesn't find the variable, it has to go all the way to main memory. And that's way slower. So core 0, L1, and then, we can assume there's probably some other caches in there, but let's just, for the sake of simplicity, let's say no. And then we have RAM. So this, they don't tell you, and we have to figure it out. That's actually part of the problem. To check between here and here is 1 nanosecond. Between here and here, it's probably like 10,000 nanoseconds. I don't know if that's realistic, but it's probably like 100 to 1,000 to 10,000 times longer to look in RAM than it is to look in cache. So when we get a cache miss, the wait time becomes so much worse. And that's why we're going to get that problem. Okay. So let's try to write two equations maybe that come up with the average time for the first scenario and then the second scenario. So let's just say f0 is the what's it called? Is the time that it takes on average for it to execute an instruction given cache hit and cache miss. So we'll say f0 of t is equal to, so we want to consider when we get a hit and when we get a miss. So we're going to get a hit in the first scenario 95% of the time. And the time it's going to take is 1 nanosecond, right? So we'll just multiply that by 1. And then for the sake, actually no, let's skip this. Let's just say the time it takes to access RAM if we get a cache miss is t. Then we know 5% of the time we're going to get miss and we're going to have to look in memory, right? How much time does it take, if it takes t nanoseconds to get to main memory, how much time did I waste getting that variable into memory? So obviously we have to do the t, right? But did I just waste t nanoseconds getting it from main memory, or did I waste more? 2t. Oh, let's assume that t encompasses both the way forward and the way back. Time it took to search. Kind of. Let's just assume all of the handling from getting the searching and all of that and like going to main memory and coming back takes t seconds. What else did it have to do before it went to main memory? Or why did it even go to main memory in the first place? Check the cache first, right? So it's pretty negligible, but there's 1 extra nanosecond that it took to first get the miss in the L1 cache. And again, that's probably, not much in comparison, but we should include it. And then likewise, we'll do f1 of t, which now, so the processor has been upgraded so that it has 97% cache hit rate. But now, instead of 1 nanosecond, it takes 1.5. So in the event that we get a cache hit, it will take on average, the 0.97 times 1.5 time, if we look at all of them, like with the weighted average. And then we know we have a 3% miss rate this time. And again, it's going to take t access because we're assuming we're using the same memory bank. And then in this case, it had to first miss with 1.5, so it's going to look something like that. Does that make sense how I got those two? It's just the weighted average between hit and miss. Yep. Okay, and then so the last thing we wanted to check was we wanted to discuss when will this change result in an improvement. So in other words, we want to check when does this function take less time than this function. So in other words, we want to check when f1 of t is less than, we'll just say strictly less than f0 of t. Right, so let's write that all down here. So f1 was this, right? Let me just pull out a calculator so that this is a little bit easier. So 0.97 times 1.5 is 1.455. 1.455 plus 0.03 t plus that times that, which would be 4.5, and then we move the decimal over 2 times. So 0.0, and correct me if I'm wrong, 0.045 is less than, and then we have the top one, so 0.95 times 1 is obviously 0.95, and then plus 0.05 t and then plus 0.05. Cool, and then we can just simplify this, right? So this plus this is 1.4, that'd be a 9, 1, so 1.5, I think? Plus 0.03 t, and then 0.95 plus 0.05 is 1 plus 0.05 t. We can subtract this to the other side, that to the other side. We get 0.5 is less than 0.0 t. We divide that. That's what, 2/100ths, so that's 1 over 50. So that'd be multiplying by 50. So that would be less than t is less than, what did I say, times 50. So that'd be 25. Move it over one time, just 25. And if you see anything that I did wrong with the algebra, just correct me on it. Yep, 25. I can even check the answer key. I have it open. It's like 4.5. They got 50. Average access time is 1.5. I think they just threw out that extra cache part. I don't expect it to be that big of a difference, though. I also apparently have the sign going the opposite way, which I think... Oh, no, I don't. I think they didn't include the cache miss part, which we should, but... I guess, does the general process make sense? Hopefully I didn't make any algebra mistakes, but if somebody sees it, just let me know. Basically just want to set up a weighted average for both and then compare them. Is the 9.7 cache faster if t is greater than 25? Yeah. Yeah, so if we go back and check the condition we were actually looking at here, this was the 97% cache versus the 95% cache. So, yeah. Which, let's look at B, I guess, too. So what this says is if the time it takes to access memory is greater than 25 nanoseconds, then the second architecture is faster on average than the first architecture. So it says, explain why the result makes intuitive sense. Well, actually I'll let you guys give that a shot. Why would it make intuitive sense that, if t is greater than 25 nanoseconds, it's better to have this machine with a higher cache hit rate than the other one? Or in other words, what does having a higher cache hit rate help me with? More accesses. Right. So that's part of it. So if I have a lower cache hit rate, I'm going to have more accesses to main memory, right? I'm going to have check main memory, right? So we're going to get more main memory. And so if we expect t is greater than 25 when we're accessing main memory more often, then, I guess I'm zooming out, whoops. Then the higher and higher the latency is between main memory and the CPU, the more and more your cache hit rate matters. So if t was 5 million seconds, you had to wait a year for it to go to main memory and back, then having a cache hit rate of 97 is way better than having a cache hit rate of 95. So the more of an impact that main memory has on a single access, the more important it is for you to not go there ever. If you graph out both functions, the second function is less likely to go to main memory over time. Yeah, right, exactly. Because it has a lower chance to go to main memory. It has a higher hit rate. Does that make sense though? The more time main memory accesses take, the higher the cache rate you have to consider. Cache hit rate you have to consider. Okay. That was the last question I had, actually. We're not that far into the section. Did anybody have any questions from either the textbook or class? If not, I'll just see if I can find something. I didn't expect to go through it this quickly. Actually, I do have one thing. Maybe. Homework? Give your thoughts on it? Did he post it on Web Campus? Emulating computer? Yeah. Okay. Let me look at it really quick. Emulating a computer. He said it would be easy, then he said it's complicated. Fair. Write a C++ or Python program that mimics the instruction cycle. Then extend that design to have interrupts in it. For fetching from memory, create an L1 cache. Yeah, you can write it in Python if you really want to. If you have the option between that and C++, I might almost just go with Python. That's just personal preference. I don't like C++. For the opcode, go with the IAS example, and for now, do a load. For the opcodes, go with the IAS example. Okay, so the one we did last week. You don't know Python? You can learn it in a weekend, but I don't know if you really want to do that. Short Python classes. Multiply, divide, and subtract. So I think you have to decode some sort of opcode from the IAS example. C# is better than Python. I don't think that's an unpopular opinion. I love C#. It's great. Can I do Ruby? Similar. Python at least. I don't actually know Ruby. Make all the widths be 4 bytes. So you can use integers to keep the data. Okay. Then for the instructions, you can still keep them as integers, but write your decode function that can convert your opcode address into an integer. Okay, bitwise operations might be useful for this. Yeah, I'll talk about that, I guess. For your opcode address combo, just go with 1 byte for opcode and 3 for addresses. Yep. This means that we can make an array vector for your main memory. As for the cache sizes, is for the first phase. At this point, we will add more features in a new date. Documentation. Oh, then I have to grade it. Cool. Oh wait, we have to implement a cache. Extend. Design. Okay. Let's just try to draft up, I guess, some pseudocode, or like what is probably needed to do this. So, honestly, I haven't lost this morning, but the example we did with the opcodes made it... Oh, yeah, that's going to be basically the same exact thing. So let's just go over maybe the functions I think you'll need. Obviously, I'm not going to write it, but I'll at least tell you what it should do. So, yeah. Let's just say you have an integer operation. Instruction's probably a good name for it. Instruction. So in that regard, maybe it is a little more difficult to do this in Python. Oh well. Yeah. So we want to basically do one thing. So in your main, or just the body of your script, if you're doing Python. And again, I'm not going to write actual C++, just pseudocode. You have a main. What you're going to need to do is fetch, decode. You can do it in assembly if you want to have a fun time, yeah. Fetch, decode, execute. Just, yeah, put it on the CPU and just have the CPU just automatically do it the way it's supposed to do. So we need to do the three things here: fetch, decode, execute. So fetch, and you probably don't want a global if you're writing it in C++, but let's just pretend that's there. You want fetch to realistically, so we'll pass it by reference, which I think Python does automatically. Some weird scoping things in Python. We want it to read an integer and then store it. So what you want to happen is just read an integer. I mean, I think that one's pretty straightforward. Just, cin or whatever the function is in Python. Will this discussion be posted online? Yeah, I'm going to post it on Canvas, and then I think Dr. Fonseca will re-upload it to his YouTube. So I guess the main thing here is that the integer is going to be 32 bits. And like he was saying, we're going to say the first byte, I think he said byte, right? I don't think that's what the IAS machine was. Yeah, he says 4 bytes. I mean, that makes sense. An integer is 32 bits, so it's 4 bytes. We're going to have that be, nibble A, so X, Y, 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 Y. Yeah, 1 byte opcode, which makes sense. I think that's similar to what it had in the book. So the first part of that, the first byte, is going to be the opcode, and then the last part is going to be the operand or the memory address. So you'll read it in, which is straightforward. Just read it in the integer, and then after that we want to decode. So what I would probably do is create an integer, pass it by reference, I guess, just because that sounds normal for C++, opcode, and then another integer for the operand. And then what you want to do, and I'll probably just discuss how I would think to do this, you want to let the opcode equal that part, and then the operand equal the other part. So let's just say as a comment, get opcode and operand. That way you can use it in the actual execute step. Let me put dots in here so that it's clear. There's some arguments that I just, you can figure it out. So does anybody have a suggestion how to easily get the opcode and the operand in one step? And he said it in the thing. There's a smart way to do it in one step. Yeah, if you're lost, that's okay. Where does he say it? I saw it. Bitwise operators might come in handy for this. So if I just want to trim and get just the first byte, and trim it and just get the last 3 bytes, is there a bitwise operation that you know of that does that? So for the opcode, we just want this part, right? Left and right shift. Yeah, we actually don't even have to do shifts. It's a much more primitive. Yeah, there you go. And I just want to and it. Which, yeah, the operator in C++ is just the ampersand. In opcode operand, and then instruction. If you're doing C++, you might want to make this a const. So the opcode, that will just equal the instruction that we get. And then if we just want the first part and we don't want the second part, then actually no, I'm sorry. Whoever said shift in the first place, you're right. And the reason is because this is a most significant bit. So if I just and it right off the bat, then it's going to have these extra zeros at the end from canceling that out. But we might actually have to do both. Yeah, and then shift, that's probably a good idea. I don't know if C++ has a shift without rotating. I think that's what it does by default. You might just want to and it first, maybe. You should be able to just shift. Oh god, and then there's the question of how do you even do that in C++? Is it just one arrow? No, I guess it is two. Yeah, you might want to just and it just in case, but in theory, just shifting this right by... So these are all 4 bits, right? So this is right here, 24. Shift it 24 for the opcode, and then, yeah. So that's probably a better idea than what I was going to do. And then for the operand, that's where we're going to and. So that one, we want to just trim off this part, right? So we'll just say instruction anded with hex 00111111. Wait, no, that's bad. I'm wrong. F. Okay. Is it clear why that works on this? These are all 1s. So when I and it with a 1, it'll just be whatever it was before. When I and it with 0, it'll always be 0, so it'll just cancel out. So, and then the last part is execute. And then that's going to be the meat of it. So, I mean, I would just take int, constant, whatever, opcode, int operand that you read in from the decode step, and then just, oops, check whatever the opcode is, and then do something. Case. And you might even be able to, if you're doing C++, do like an enum at the top, or say like define add 0, define, just do like preprocessor directives, subtract is 1, whatever it corresponds to with the IAS machine in the book, and then say like case add, add break case sub, do whatever, subtract. I know it's probably hard to see all this, but does that make sense? The general idea for that? I think this would be an elegant way to do it in C++, so that you don't have to sit there and keep checking in the book. You can just write this all at the top and then have it. Seems a lot more doable, hopefully. And any idea how he wants us to implement omdals? Would be just... Does he want... I didn't actually finish reading it. That's my bad. I think he wanted you to do caching, too. You might also have to simulate main memory. In that case, I don't know. Just make, like, an integer array and just call it memory. Make a calculator for omdals. I think that would be straightforward. I know he said that as, like, an example. I don't know if he wanted it done. For your opcode address combo, just go with 1 byte. Yeah, we figured that out. This means that you can make an address vector list of size 2 to the 24th power for your main memory for now. Oh, yeah, this is exactly what I was just saying. He would eventually want us to do omdals. I think it would just be an example of calculate amdal's law, which in that case you could just use that one function that we wrote. Math function, not C++ function. Yeah, so I was right. Just make an array called memory, and then that's your memory. So whenever you get an operation, you'll reference this. In that case, I would say maybe make a class or make this global for memory. Even though they tell you not to use globals, C++ is kind of strange and it's hard to get around it sometimes. As for the cache size, experiment with different cache sizes. Cache hit or miss. How would emulating cache work? Yeah, that's a good question. I have an idea, but... Can you show your execute pseudo? Yeah, I'll go back to it in a second. It's basically just one switch statement. Yeah, we did chapter 5 yesterday. I think he'll post it soon. I put it up on the website. Or the Canvas. Eventually we will want to make this work and be able to load a tiny program and basically work through it. For the first program we test this with, we will make... Oh, so you'll write Amdahl's law in IAS and then use your virtual computer to compute it, I think. Fun. Will the cache just be a smaller array? Yeah, probably. This due date is for the first phase. At this point, we'll add more features later. Yeah, I'll just give a suggestion as to how I think I would do cache. So somebody said just make another array, and I think that's smart. Here's the execute, by the way. It's just a switch statement. Check the opcode. Figure out what it corresponds to. So I gave enums, like add, subtract. You would just keep going, like load, store, all that stuff. And then you would do whatever that operation actually is. Yeah. So I would write maybe one more function. I would also have another... I'll try to take a screenshot of this whole thing if I can and post it in the Discord. Int cache, because I know it'll be hard to see on video. And then I would just go down here and then write another one that's just like int get variable. And then no, we probably want more to cache actually. I don't know how accurately he wants you to simulate it. The easy way I would say is just use a dictionary. I assume there's an easy class for that in C++. And then just store the address as like an integer and then the value as an integer if you know how to use dictionaries. But you could always write your own class that does like a linear search through an array. Load everything into the memory array and then only work off the cache array. So we'll just go over what I think you would want to do for this. So int get var, we'll just say int address. So what we want to do, so I'm going to try to simulate this like cache the best I can. Oh, whoops. I don't know if I recommend doing this because your debugging process is going to be like way worse if you just write the same thing I do. So we want to check cache. So the thing about cache, right, is that it's going to be smaller than memory. So not every variable in memory is going to be found in cache. Maybe we'll just add this here, like initialize memory. So the problem is I wouldn't do this as an integer array. What I would do is either make a dictionary if you know how to use it, because I think that's the easiest way, and it'll be pretty faster than I think the easy implementation would be. Well, actually, definitely faster. I would just make a class or a struct called cache, and then integer array tag, and an integer array value. What do they call it? Data in the book. And store the address. In this case, let's just say the address is the index into this array. Store that tag whenever you do a cache miss and have to fetch it. So if I was to like have the memory array, I'll do this on a different page in a second actually. Memory array, and I get a cache miss, I'll go get it from memory, store it in the cache, and then return it. So your get variable, let's just finish that really quick, is just going to mimic cache, or like how you would do check cache. If you get a hit, then return the value. And you're probably going to have to do a lot more than this too, actually. You'll talk about this next week, hopefully, but you'll need a way to replace values in the cache. I guess that should be a void. You'll need a way to replace values in the cache as well. I may even just call this insert. Because if the cache gets full, you're going to have to think of a way to replace it. And that's, Dr. Fonseca will go over that next week. You need to come up with a heuristic that determines when it's full, which one should I replace. The easy way to do it is just check which one's the oldest. How you do that, I guess, is up to you. But, yeah. So if hit, return the value. If miss, check memory. Well, it's going to be in memory. Get it out of memory. And then copy to cache, and then return it. And so the thing I was saying, if you want it to be accurate, but don't actually do this probably until you're done at least. We would sit here and I would throw in a sleep function here for like 2 seconds. Or 2 milliseconds, I guess. Let's just say 200. That way when you get a cache miss, you have to wait longer. How will we know if you miss? Well, if you don't find it in the cache. So what I would probably do, just to keep it simple, is I would check. So this tag here, it represents, just for the sake of keeping it easy and not doing all the extra calculations, unless he asks you to specifically do this, I would keep an integer array of all of the addresses. Actually, yeah, let me do this over here. Here's the implementation I would think to do. I meant to do this. Memory array. We need a count variable for hit and miss. Yeah, that would be a good way to do it, at least in the cache class. I think that's a good idea. Otherwise, you might be able to initialize the cache to a sentinel, like null, let's just say, and then check, is there any null space for me to put it in, and then just put it in there. But then I guess it's more like a heap, and I don't think that's actually how the cache works. You might want to actually do the whole modulus, like hash it into the cache table. Array for ... n-1 n. So memory is just going to contain, random variables. And these are all just integers, right? B, C, 0, 5, 1, 4, and then, whatever's in the rest of these. So cache is going to be much smaller, and if we want to simulate the way actual cache works in this virtual computer, so it's going to be much smaller. Oh man, and then there's up to you if you want to do like a block size, in which case I would make the cache array a long. Yeah, there's a lot left up to how detailed you want to go with this implementation. And then we could load 2 integers at once and then figure it out. Yeah, that's way too much. Let's just keep it as an integer. I think this way we don't just overwhelm ourselves. So this implementation I'm doing is a little unrealistic, but it's just, let's not just go crazy with it. What I would do is create either a hash table. Actually, a hash table might even be kind of easy. That also simulates cache pretty well. So just come up with some sort of cache size, integer cache size. I think this would be a lot easier. So come up with some constant cache size, or calculate it at runtime based off the memory that he gives you. This slowly just gets more complicated. Yeah, the caching is where this gets hard. What I would do, hopefully this will be straightforward in a second. What I would do is, so the processor, let's just say, gets the operation, or your virtual processor, your program, gets operation hex 0 to 00004. So this is the opcode, right? This is the operation. What I would do is do the decode that we figured out earlier. So it figures out that's the opcode, that's the operation, puts them in 2 different integers so that you can use them. And then when you go to actually execute this, figure out whatever 2 is. Let's just say it's add. We want to add to from memory address 004. So what I would do is I would first look in the cache. And then if we're doing a what's it called? A hash function, we're just going to take the operand, which is 4, and then mod it by the cache size. Figure out where we should store it. So in this example, what part of the cache is memory address 4 going to correspond to? Which one of these? 0, right? So then we take this, 3, 2, A, C, B, F, and then we store it in index 0. So you just say integer or cache sub 0 is equal to cache sub 4. So the easy C++ for that would just be we say something like if miss, if you figured out you had a miss, cache sub operand mod cache size. Equals memory sub operand. Because the operand in this case is just an address. So what I'm saying here is hash it into the cache, find the index that would make sense using the hash function, and then copy the memory location unhashed into there. So like in this example, if I had 4, I would say, well, I had a cache miss because it wasn't initialized yet. I'm going to store in position 0, which is 4 modulus 4, the size of the cache that I had there, and I'm going to store address 4 into it. So it gets put into there. And then let's just say, for the sake of this, that the next operation you get is hex 03 0 0 0 0 1 2 3 3. Not a fan of cache. It's important to at least be aware of it, I guess, as a programmer, but all this stuff about hashing and stuff, I don't think you'll necessarily use unless you're like a systems programmer. I am definitely not. BCA4. So let's say the next operation I get is this one. Again, what your programmer is going to do is it's going to fetch this, and then it's going to decode this, figure out this one is the opcode, this one's the operand. So it's going to say, well, I need to do memory address 3 now. So I look in the cache first. So I figure out the hash for this one. So let me just write some things off to the side here. So the hash for this one was 0. The hash for this one would be 3, right? 3 mod 4 is 3. And then let's just create a column really quick for hit. And then this one was a miss, and this one was a miss. So what I would do is I would go to memory, I would look here, and I would say 3, I'm going to copy that into the hash location in the cache, which is here. So I would say hex df bca4. And then let's just say for the next operation I get 0 5. Whoops, I should write out the whole thing. 0 0 0 0 0 8. Let me just write that down here. 8 hex 5 6 4 D. No, let me do something else first. Well, let me at least populate it. We'll come back to it. EF. So let's say instead this was 4. And this whole time I probably should have been keeping some extra stuff. A tag. And all the tag is, just to clarify, is where we originally got this from. So this was address 4, right? This one was address 3. So you should keep track of where the original memory came from. Why are things in memory only 24 bits long? Good question, because I forgot to write it all. It'll be 32 in reality. Thank you for pointing that out. I guess I just forgot to write it. It should be 32. That's my bad. I just tried to fit it in the box and I wasn't paying attention. Yeah. So let's say we get this next operation. We again decode it. 05004. Okay. So the question on this one is, so we have opcode 5, operand 4. We're going to check the cache first. Are we going to get a cache hit or a cache miss? You're right. We're going to get a hit. So what the operation is going to do is we're going to first check the cache, see if memory address 4 is there. We loaded it earlier, so it is there. So we can just get it from the cache and return it. And we could have just checked hash location 0 and then checked the tag at that point. If that one's a hit, we didn't have to do anything out of memory. I'm going to re-go over this in a second just to make it more clear, because I know it can be really overwhelming with just, 2 pages worth of stuff just everywhere. So let's say we get hex 2000008. Okay. So first off, the opcode, again, assuming we fetch and decode, the opcode for this one is going to be 2. The operand is 8. So first off, what is the hash if the size of our table is 4? What is the hash for that one? 0, right? So we're going to go look in the hash table that I have here, and we're going to check 0. So that's the location that if memory address 8 was in the cache, it would be there. It would be at hash 0. And we'll look at it and we'll say, does the tag match the current one? So does the tag here, the address we originally got it from, match the address that we want to get stuff from? And the answer to that one would be no. Yeah, right? No. It didn't match the tag. So that means that this is actually a cache miss. There's something already in the cache, but it's not what we want. So what we're going to do is we're going to lose this, overwrite it, and replace it with the stuff that's at memory address 8. So this now becomes hex 56FDEF, and the tag becomes 8. Does that make sense where that one came from? And I'm just going to run through the program again really quick just to clarify everything that's going on, because there's a lot of stuff going on right now. So really quick, let's just look over this one more time. So again, let's assume that this is our program. So this is whatever you're reading in from the user. What you're going to do is read through each one. So we're going to fetch it, so C in it basically, and then split it into the opcode and the operation like we showed on the other page. At that point, we need to actually execute it. So whatever this means, add, subtract, whatever, we're going to do that. But we need to get the variable that it works on first, which is described by this. This tells us the memory address of the variable. So on the first one, we want to do something to memory address 4. So let's just re-erase the cache here. In fact, let's just redo a large portion of it. So we want to do something with memory address 4. Oops, let me finish erasing this too. So what we should always do first is check cache, see if the variable is in there. So to quickly do that, let's hash this address by the number of things that are in the cache table, which is 4. So again, what's going to be the hash for memory address 4? 0, right? And then we go and we look in the cache at address 0 or index 0. Again, these addresses, for the sake of your C++ argument, you just might want to be indexes or indices into an array, just to make it easy. Are we going to get a hit or a miss? Is it in the cache? Miss? Yeah, most people seem to be saying miss. And you'd be right. It is a miss. Is that clear as to why? There's nothing in the cache right now. We're restarting the program. So this is a miss. There was nothing in there. So it missed. So what do we have to do if we miss? Go to main memory, right? So we go to main memory, we load it, and again, this was address 4. So we go over here, and we say, well, we need to load the contents of 4 into the cache so that maybe, if we're lucky, later we'll come up with it. So we load that in there, and then we'll just store a tag. In this case, to make it easy, I'm just going to say store the actual memory address. Not realistic again. It's probably smaller. And it's usually like the most significant bits, but just for the sake of making the program easier, because it's already kind of hard, we're going to store it there. And then the next one, we fetch, we decode, we figure out that the opcode is 3, the operand is 3. So first off, what's the hash for this one into the cache table? Three. Yeah, you're right. So it'd be 3, right? Because 3 mod 4 is 3. Then if we go and look in the cache table, or the cache, is there going to be a hit or a miss? Are we going to find the value? Miss, right? So it's not there. And then again, just to go quickly, because I know we're almost out of time, we're going to have to go to main memory again, right? Copy that. Hex df bc a4, and then we'll store a tag of the memory address we got it at. So let's just do these last two, and then we'll call it a day, and I'll try to post big screenshots of these. So what's going to be the hash value again? So I fetch decode, I get that the opcode is 5, the address is 4. What's going to be the hash for this one to look into the cache? 0, right? So I look into the cache. Does it match? Yeah, hit. So this one's a hit because we already in the cache have memory address 4. The tag matches. So when you're actually implementing this, you want to check if the operand matches the tag, and if so, it's a hit. And if not, it's a miss. You have to go to memory, do the copy. So we hit, we just keep executing the program, we don't have any extra overhead. And then last step, again, we fetch, decode, we figure out that the opcode is 2, the operand is 8. So where does this hash into the cache? Zero again, right? And is this one a hit or a miss? So we go up here and there's something in the cache table. Right, but it's a miss. And the reason being is because this tag, this address, doesn't match the actual tag of this one. So even though there's something hashed in there, it's not the correct one. So again, that's a miss. So we'll have to go to memory, overwrite this with address 8, which is hex 56 FDEF, and then replace the tag with what we actually put in there. So you only want to set these values on a cache miss. On a cache hit, you just grab it straight out. So even though this was a miss, but something was already in the table, we do the same thing as if there was nothing in there anyways. We overwrite the value in there, and we overwrite the tag. And for your C++ program, maybe you want to initialize all this to null and all this to something like -1, so you can, make sure that it makes sense. All right, so I think we're at about time. If anybody has any questions, let me know. I'm going to post these screenshots, and then the video should hopefully be up soon. So if memory location 4 was saved to cache, then location 8 was saved. 8 would overwrite 4. Yep, right. Because, yeah, they both mod to the same thing. So that's the problem with hashing. If you don't have a really specialized hash function, you're going to have collisions where it overwrites one thing. And then if we were to use address 4 again, we're going to have to go retreat it, or re-get it from memory again. You mentioned to experiment with the cache sizes, so we just keep adjusting cache size to whatever's the most hit. Kind of, but you don't want to make it the most hit. I guess the point is to just see the difference between a large cache and a small cache. Because if you make it too big, you're going to get a 100% cache hit rate, and that's not realistic. But yeah, just make it some number. I would make it for sure smaller than memory, though. Wouldn't you want to fill the whole cache before overwriting? Ideally, but the thing is, we want to make lookup really, really quick by doing this hash. So, yeah, we don't actually end up filling 1 and 2. So that is a problem, but it's much slower if we try to fill the cache first. We wouldn't have a hash function to immediately just go look and have, if you're familiar with time complexity, O of 1 time, we would have to instead do a linear search through cache, figure out what's not initialized, potentially have a bit that actually specifies whether it's been initialized or not, and then that, that's a lot of overhead, because it happens every time we do a memory access. So O of n every time is worse than O of 1. The 135 was outputting hello world. See, you can write a program that does hello world and then have your virtual machine print hello world. It's great. It's meta. And actually, to answer the question further from earlier, if you had that structure where you were to fill it first, that's a heap. And this is a hash table. So they're different data structures. Hash tables, yeah, 302, which I'm not sure if everybody's taken. I know some people said they knew time complexity, so yeah, probably not. I would imagine not. 3 years ago, I might remember some of it. This looks like an ed assignment. This does seem like an ed assignment. It's very hard, but very practical, in terms of at least learning something. Like, oh, he has you do MIPS. Huh. Do we get input data? Maybe. If he doesn't, I'll maybe just post some in the Discord chat. You're going to have to write your own input data for the latter one, though. But I'll probably just write it so that everybody's like clear what it is that you're supposed to be getting out. x86 is better. I thought MIPS was easier, but I might just be crazy. Which is strange, because, it's like a RISC architecture. Alright. Any more questions? If not, I'm just going to post these. Well, the input machine code, it'll probably be from a file, but you can just expect it to be from standard in, I guess. Yeah, the due date is for the first phase, which I think is just including the fetch, execute, decode, and the cache. And then he's going to have you write a program for this virtual machine that you wrote later. Alright, sweet. I don't see any more questions. So, unless somebody had one, yeah.
Do I get bonus points if I write it in MIPS?
Probably not. You're just gonna get a headache.
Oh, then. Maybe it's not worth it then.
No, just write it in a high level language.
Yeah.
He said C++ or Python. I would kind of think it would be easier in C++, but that's just me.
Okay.
All right. Well, everybody take care. Oh wait, why do you think that? Why do I think it would be easier in C++? I just think classes are easier, and I think it would be nice to have a cache class. I mean, I would write it in C#, but he didn't give that as an option. But I just like C#, so I don't know. Yeah, you'd have to do your own memory management in assembly.
I meant uninitialized.
Oh, you just like initialize it to the program?
I would just make a space of uninitialized memory and use that.
Yeah. Yeah, that would probably be what you'd have to do. Just give a size and a pointer. Alright, well I think on that note, I'm gonna bail, but if anybody has any questions later for the assignment, I guess just message me on Discord. I'll probably be around.